Okay, another concept that we come across in integrals is this idea of U substitution. If we look at sort of the references of integrals that we've had to look at and all that sort of thing, we'll notice everything talks about doing things in terms of U and not necessarily. You might ask, well, why didn't they just use X? We're almost always integrating with respect to X, or maybe with respect to Y or respect to time or something like that. So why would they use U? Well, one, obviously, so that you don't get confused and think that you can't do X or Y or T. But the other idea is to think about this idea of U can be more than just a single variable. It can be a quantity. So for instance, if we had the integral from, I'm just going to say from 0 to 3 of 3x plus 4 squared dx. So one way we could do this would be to expand it. And if we have a perfect square, we would end up with that. And then we can just do each part. We know how to do this integration by this time, and so we can follow through that process. So we would, polynomials, we'd raise each power by 1 and divide by that new power. We should also simplify and reduce that, but I wanted to make sure you understood where all these numbers were coming from. So we could simplify that next. And then I would just have to plug in my points like we've done in the past. Put in 3, evaluated at 3, and evaluated at 0. And by, evaluating at 3, simplifying those, evaluating at 0, I get 0. Simplifying those answers, adding them together, I could get to 273. And that's not bad if I just had to square it, but I want to show you a different way we could get there. We could instead think of this in terms of U substitution. So with U substitution, what I want to do is, instead of breaking everything apart, is I want to think of this as one big interval of things. So I'm going to let U be that entire expression. So if I let U be 3x plus 4, and then what I also need to know, remember, whenever we're doing our integrals, we're going from we have to have an integral with respect to U du. So I need to get what du is, which is the derivative. And of course, if I take the derivative of this, I just get that it's 3. So now I could rewrite my expression. But before I rewrite it, I should be clear that, remember, we took the derivative of this with respect to x. So this du, this is 3 dx. Or the other way to think about that is by taking the derivative that du dx equals 3. And then I just kind of multiply both sides by 3 to get back to this. Or, I'm sorry, multiply both sides by dx to get back to this expression. But du is going to be 3 times dx. So now I want to rewrite this expression using u and du. So when I rewrite that, there's a couple things I've cheated in here. Notice I put a 3 dx in here, and I only had dx to start with. So that means to balance that out, I must multiply by 1/3 to balance, to keep that in balance. The other thing you're going to notice is that I've ignored, or we're not going from 0 to 3 anymore. Because technically, well, this is technically still true as long as we're going in terms of dx. So that's okay. I'm still going from 0 to 3. We'll talk about how that would change in just a second. All right, so now I want to go ahead and do that substitution to make it look like u du. So now I think we can agree that I have my expression of 3x plus 4 was u. So this is u squared. This is du. I still had to keep that 1/3 out there because I had to create that to balance things out up here. So I have that 1/3 out front. This is where I've actually left these blank. And the reason I've left these blank is because technically I'm not going from 0 to 3 anymore, because that's what I was going to with respect to x. I would technically have to go from whatever x equals 0 means u equals something, and x equals 3 means u equals whatever those limits are. And so I could figure those out, but generally what I'll do is just do the integration and then put it back in terms of the x terms after I'm done. So just to be clear, so I'm ignoring these here. So again, I'm going to ignore them for now because it's not important. I'll get back to using x's by the time I want to evaluate the function. But if I had to, I would have to plug in those x values into my u function, and so I would actually be going from 4 to 11 on the u scale. But again, let's just do the integration and then talk about that. So how do I integrate this? Well, if I'm looking at this and integrating with respect to u du, well then it's just a simple power rule, right? I'm going to raise the power and divide by the new power. So I integrate using u, I get u cubed divided by 3. So now I want to and this would really be from u1 to u2. Like I said, we found out that those were 4 and 11, but for now I don't want to really deal with that. Then I want to retranslate that back into my x terms by substituting backwards, by substituting my expression for u back into this place. So when I do that, I replace the expression. I've got my x plus, I'm using x plus 3x plus 4 for my expression now, so I can take these back to being what the limits were, what my endpoints were for x values. I don't have to worry about doing the translation anymore. And then I can evaluate that. So again, we can work through that. So there, I plugged in 3 here, I plugged in 0 here. I can work those parts out. If I was smarter, or if I wanted to be more efficient, I probably could have pulled the 3 out to start with and not had to divide both of these, but we'll keep going. And so if I work that part out and simplify it, you'll see that I get back to the same answer. And more to the point, even I did this all out numerically, more to the point would be if I just did the integral, these are also the same. If I took this expression and expanded it, which is a little bit harder to do expanding a cubic function, I would end up with this same expression. Once I took into account the divided by 3's in there, I would end up with this same expression here. And you might say, well, that's a lot of work when it was a lot easier to expand it. And that's true for a case like this where it was just this squared and we moved it up to cubed. But when we get to even bigger expressions, like if it was to the 5th power, well, doing that expansion would be very ridiculous. But on the 5th power, this is going to be the same amount of work. So this is one way U substitution works, and it's not just a matter of polynomials. The thing that I'm using in there can be any sort of expression. You'll see some examples in the homework of other things that might look like that. Another example where this might show up is you see expressions like this come up a lot of times where you have e raised to a power inside of an expression, but you've also got e to that same power outside the expression. And that's helpful because if we think about letting this part be u, then what is du? Well, let's see. So again, if we let u equals minus 1 minus e to the negative x, then the derivative would be that part goes to 0. This, remember, when we take the derivative of e to a power, it's 1 over that, the coefficient of that, and the e part stays the same. So 1 over negative 1 e to the negative x. Negative 1's go minus the negative 1 becomes positive 1, 0. So actually we've got the u would be, sorry, I lost my dx term over here, but du would just be e to the x dx, or e to the negative, sorry, e to the negative x dx. So this expression already sets up as the integral of 1 minus e to the negative x, e to the negative x dx. It's already set up perfectly. We don't even have to make any adjustments like throwing in a factor of 3 or anything like that. So this is du, this is u, so I know this is going to be the same as 1 minus e to the negative x squared divided by the new power. Because it's just going to be u squared divided by 2. So that's another time it comes up. Again, you'll see several places where this just kind of comes along. When you start recognizing sine and cosine being with with sign differences, but sine and cosine being derivatives of each other. A lot of times you'll see that if you have to integrate sine x times cosine x. Well, if this is u, then that's du. And I guess technically, if it's cosine x, it's going to be negative that. So we'd have to get a negative sign involved there. But yeah, again, so that makes things easy. So when we integrate that, we can just end up with a cosine squared term and those sorts of things. So U substitution, a very useful tool in helping us solve some other problems that we'll come across in integrals.